Thank you very much. Thanks for the invitation and thanks for the opportunity to be here. So this is the first time I'm talking about this work, so I hope it goes well. So anyway, I'm gonna start with some motivation, and let me know if I write big enough or if you have any questions at any time.
I think it's good.
Yeah, okay. So some motivation. This is basically like minimal model program stuff. Some preliminaries. So defining more or less, not really defining, but saying what a Sarkisov link is, saying what a Mori fiber space is, what a weighted blowup, and so on and so forth. And finally, some results. So, so I'm going to do everything over C. And so suppose W is some smooth uniruled projective variety. So this is not a big assumption because you always have a resolution of singularities. So you can assume your variety is smooth and projective. So by BCHM, you have that your variety W is covered by rational curves. That's the meaning of being uniruled. So if you input it into this machine called MMP, then what you get at the end of this process is a Mori fiber space. Okay, so I'm going to define Mori fiber space in a second, but this is just to say that what MMP does really is to try to come up with a good representative of your birational class. So good in some sense that it has some kind of nice properties and nice singularities, and it's a good representative in that sense. So MMP tries to find a good representative of your birational class. So the point is that remark. So even though for a uniruled variety, for instance, you have a Mori fiber space at the end of your process, at the end of your program, it's not true that the output of your program is unique. So for instance, actually, let me write it as example. So if you take S to be a cubic surface, then we know that this is rational. It's the blowup of P2 in 6 points in general position. So P2 is a good representative of this variety of the cubic surface. But so is any, here's a Brooks surface. When n is bigger than 1. So the representative of your birational class, I mean, even though it's the n product, even though all of these things are n products of minimal model program for uniruled varieties, it's not true that they are unique. So there's an in fact infinite number of representatives in general. So representative, not unique. So because the representative is not unique, it's kind of natural to study the relations between these representatives. So what we want to do, so goal, well, a general goal is to study relations between n products. And I'm really focusing on the case where W, the variety we start with, is a uniruled variety, so that we end up with a Mori fiber space. So in general, this is a very hard problem, even though there are some tools and strategies and techniques. But let me go bit by bit. So let me make a definition. So what is a Mori fiber space? So you take sigma to be this morphism from Y to B. So morphism of normal projective varieties. With connected fibers. so this is also subjective. Sorry, morphism of normal protected varieties. So this is called a Mori fiber space. If certain conditions are satisfied, so the total space Y has Q factorial and terminal singularities. So again, if there's some words that I'm saying that are not clear, just let me know. Okay, minus ky is sigma ample. So this just mean I'm just meaning that the fibers are Fano varieties. Yeah. And finally, we want the dimension of the base space to be smaller than the dimension of the total space, and the relative Picard rank, which is the difference between Picard ranks, is 1. So this is what a Mori fiber space is. So let me give you some examples. So we've already seen some, but okay. You take sigma to be Pn fibered over a point. This is kind of a trivial example. We just look at this Mori fiber space as, just call it Pn. So obviously it has Picard rank 1. Yeah. Another example we've seen is these Hazelbrook surfaces. So, okay, I've defined it before. So these have morphisms to P1, and the fibers are also P1. So they have a P1 bundle over P1. So fibers are P1, so they are Fano. And the relative Picard rank is also 1. So we also have some, so for instance, for some hypersurface of degree D, so let's say smooth hypersurface of degree D in Pn. This is also a Mori fiber space, provided then that n plus 1 minus d is bigger than 0. So this is just the Fano condition again. So these are relative Fano varieties, and these are the absolute Fanos. But okay, these things are not really important. You just have, they are all Mori fiber spaces. Okay, so there's a really nice theorem that says, well, so again, we want to study relations between different endpoints of the minimal model program, provided that they are birational and they are Mori fiber spaces. So there's a structure theorem that says that explains what a birational map between two Mori fiber spaces should be. Okay, so this is what I'm going to state now. So this is due to Corti, 95, and by Aiken, McKernan, I think 2014, but I'm not super sure. So this is, Corti did it for 3-dimensional case, and Aiken McKernan for n-dimensional case. So they say that any birational map between Mori fiber spaces can be decomposed as a finite sequence of Sarkisov links. Oops. Okay. So the point is, to study the relations between two birational Mori fiber spaces, we have to understand Sarkisov links between them. So this is where the title comes from. So I want to study relations between P4 and all the other Mori fiber spaces that P4 is birational. Not all other, but some other Mori fiber spaces that P4 is birational too. And for that, I need to understand Sarkisov links from P4. So what does a Sarkisov link from P4 look like? So a Sarkisov link from Pn looks something like this. So you start with your Pn. You take some divisorial extraction from Pn to T0. Then after, you have some other birational maps, T1, Tn, and then it goes to X. So I'm going to define this in a second. So what are these maps? So phi is some divisorial extraction. Tau I are small q factorial modifications. So this means isomorphisms in codimension 1. In particular, they don't change the visors. And phi prime, phi prime can be either fibration, a fibration in the sense that phi prime is a Mori fiber space, or a divisorial contraction. Okay. So this is what we have. This is what a Sarkisov link from P4, from Pn, in fact, will look like. So first we start with the divisorial extraction. We do a bunch of small modifications, if any, and then either fibration or a divisorial contraction. But there's a rule here, which is, oops. There's a rule that each step, and this is really the point. So each step is q factorial and terminal. So we need to ensure that all these maps will give you varieties that are q factorial and terminal. So this means that they are in the Mori category. Okay. So I think the most important remark I have to say today is that so controlling is controlling with 2 L's or 1 L? Probably 1. Not sure.
I guess 2.
2? Okay. So controlling the singularities of, throughout, so controlling the singularities along the way will obstruct the existence of the Sarkisov link. So what happens, and what can happen in general, is that, well, you do a bunch of birational maps, a bunch of contractions, small modifications, and so on, and at some point you have one that goes out of the Mori category. So it gives you singularities which, for example, are not terminal. So this breaks the link. This is not called a Sarkisov link anymore. And so you really have to ensure, and this really bounds the possibilities of Sarkisov links that you have. This is the point of the remark. So, okay, so the question is, when do you have a Sarkisov link? So there's this nice theorem by Aban and Kalogidus. But I think there's okay. I mean, I think pretty sure they're not the only source for this, and they say something really nice, which is Suppose that T is some divisorial extraction with some fixed center. Okay, so you extract a divisor from some fixed chosen center from Pn. And suppose that you have, okay, I'll go to the next page. And suppose that you have the following three conditions. So suppose that T is a Mori dream space. Suppose that suppose that Ti, so the way I defined them before, so the Ti's are these guys up here. Let me call it T0. So Ti's are terminal and Q factorial. And suppose also that minus K, the anticanonical divisor of T, is actually in the interior of the movable cone of T. Okay, then there is a Sarkisov link. And moreover, it is unique. Okay, so there is only one such decomposition starting from a divisorial contraction on that center, if this happens. Actually, this is an if and only if. Okay, so of course in our case, because we're starting with P4, this is automatic. Because T is toric. So this is one thing that we don't have to check. Okay, so let me write our specific problem here. So actually, any questions so far? Because this is like where I start going really into the thing. Okay, so the problem here is, suppose that I have some divisorial extraction, which is a weighted blowup. So an ABCD weighted blowup of a point. Oh. Of a coordinate point. So find ABCD such that phi initiates a Sarkisov link. Okay, and we know what we have to do. So we know the conditions that need to be satisfied. So we need to guarantee that Ti's are terminal, and we need to guarantee that the anticanonical divisor of T is in the interior of its movable cone. Sorry. Okay, so I'm going to define this. I don't think everybody's familiar with it. So I'm just going to define a weighted blowup at a point. Suppose that you have an n-tuple of positive integers, okay, and you define C star action on Cn plus 1, which goes like this. So lambda an xn. Okay, now I'm defining a toric variety, which is T Cn plus 1 minus the irrelevant, so minus the origin. so x1 xn over c star. Okay, this is a variety. So this is a toric variety. Okay, so now I define the map phi that goes from T to Cn, taking U, x1, xn, going to U x1, U alpha n, xn. Okay, so this is by definition the weighted blowup of Cn at 0. Okay, so what we did was simply we took a particular C star action on Cn plus 1. Okay, we defined a toric variety upstairs using this action, and we defined a map to Cn. Okay, this particular map is called the weighted blowup of Cn at the origin. Okay, so there's a nice way to represent T, and we do it just by this matrix. Okay, so this just denotes the action on Cn plus 1, and this little bar here in the middle just tells you that, well, the locus that you took out to build the quotient is x1 up to xn. So these are variables u x1 up to xn. Oh, xn. Okay. So is this clear? Okay. So what I want to do now is not do this in Cn, but do it on Pn. So we can really do the same. So we can do the same on Pn. So let me give these names for the variables. So in this case, T is given by this matrix: 0, -1, 1, 0, 1, 1, alpha 1, alpha n. Okay, so again, what does this mean? So we have two independent C star actions. So on the first row we have, so this is x1 xn, x0 u. So you can see on the first row you just have a C star action on Cn plus 1, well, n plus 2, but this is just a C star action defining the projective space. Okay, this is so the first row, the C star action defining Pn. Okay. On the second row, this is just a different C star action, independent C star action defining the blowup. Okay. So, and again, we define T. So this is just a representation for T, but T is really defined to be Cn plus 2, plus 2. Take away, did I say take away? Yeah. So take away u x naught union x1 up to xn over these two C star actions. Okay, this is a rank 2 toric variety, which is the weighted blowup of Pn at the point. So let me write it. Weighted blowup Pn at px naught. Okay. Okay, so what we have to understand is the singularities of this guy. And maybe I won't go into too much details because this is can be very messy. But let me kind of make an example. So suppose that I have T, a very particular case given by this. So maybe you can see that this is the blowup of P3. So on the first row, you have the action on C4 defining P3. And on the bottom row, you have the action defining the blowup. So this is a 1-1-3 blowup of P3 at the point, at the origin. So 1, 0, 0, 0, 0. Okay, so you have, let me give it variables to this. And you have the patch, what's the patch? X0, X3, different from 0 to be isomorphic to 1/3 of 1, 1, 2 singularity. Okay, so if you want, maybe I give you just slightly more details, and I can say that. So this patch, this is isomorphic to spec of C U X0 X3 1 over X0 1 over X3. So all the regular functions on this patch, which are invariant under this C star dot C star action. Okay, so if you do some computations, this is spec of, let me just write this down without doing it. So after some assignments, you can write this as xz, yz, z cubed, x cubed, squared y, cubed. Okay. And you can see that this is the spec of Cx, y, z, which is invariant under this group action. So this is a finite group of order 3. This is the third roots of unity, which act on A3. By the following. So epsilon is some primitive generator of this cyclic group of order 3, and it acts like epsilon x, epsilon y, and epsilon squared z. Okay, so you can see that these are exactly the invariant monomials with respect to this action here. Okay, so in particular, this is the definition of a 1/3, 1, 1, 2 singularity. Which is a very fine terminal cyclic quotient singularity. So the a 1-1-3 blowup is all good. So we can perfectly fine do. We can perfectly well do a 1-1-3 blowup of P3 because this ends up being terminal. At least the first guy ends up being terminal. Okay. So I want to explain now how to get the other TIs. Actually, how do you get the rest of the link? Because so far we just did a weighted blowup and nothing else. So for that, I have to talk about cones in T. Okay, so there's several cones in T. Let me start with N1T. This is a finite dimensional vector space of Q divisors over numerical equivalence. So this is a finite dimensional vector space, and its dimension is equal to the rank of the Picard group of T, which in this case is 2. Why? Because the Picard of T is, well, it's generated by H plus E, where H is just a pullback of a hyperplane section away from the point that you blow up. Okay, this is kind of abusive notation, but you know what I mean. I have a hyperplane section on Pn, I pull it back, and let me call it H. Okay, they're isomorphic in time. because the hyperplane is chosen away from the plane. So that's all fine. Okay, so inside this vector space of this two-dimensional vector space, I have a few cones. So I have the Neff cone of T, which is inside the movable cone of T, which is inside the effective cone of T. And of course, this is inside N1 of T. Okay, so example. So we started with, let's look at our 113 blowup of P3. Oops. What are the so N1 of T has this very natural decomposition, and the question is, what is it in this case? So T was 0, -1, 1, 0, 1, 1, 1, 1, 1, 3. So you can read off the cones from here. So this is U, x0, x1, x2, x3. And let me just say that the exceptional divisor is given by U equals 0, and it's isomorphic to P1, 1, 3. So this is my exceptional divisor. So it has array 0, -1. This is my H, pullback of a hyperplane, which has degree 1, 0. Then I have x1 and x2, which have degree H minus E. And finally, I have x3, which has degree 1, 3, which is H minus 3E. So let's see if I can do this. So this big thing is the effective cone of T. In yellow, I have the Neff of T, which happens to be equal to the movable cone of T. Okay. Now, the anticanonical divisor of T is just the sum of the effective divisors given by the coordinate hyperplanes. So this is just I just need to sum all these guys here. Okay, so this is 4H minus 4E. Okay. Okay. Which happens to be not in the interior. So this is not, so, sorry. So this is not in the interior of the movable cone of T. So let me write it here. So this is minus KT, which is 4 times that guy. So it's exactly in the boundary of the movable cone. And because of that, we don't have a Sarkisov link anymore. So the reason, the real reason that we don't have a Sarkisov link is that at the end of the link, you have a divisorial extraction to a canonical singularity, because the anticanonical divisor is in the boundary. Okay, let me give you an example that does give you a link. Okay. So now we go to P4, and we have 1, 1, 2, 2 weighted blow up of the origin. So 1, 0, 0, 0. So T is represented again by this matrix. It's a C star dot C star action. Okay. Let me write again what the effective cones, what the decomposition of the effective cone is. So it's E, H minus E, sorry, H minus E, and H minus 2E. Okay, so there's a little bit of a difference now. It's if you look at it before, you know that the Neff cone is equal to the movable cone in this case. So this doesn't happen anymore. So the point now is that h minus 2e is movable. Okay, but not Neff. So what are the colors again? Let me do like this. So this is the Neff of T. And this is the movable cone of T. So this is movable. I mean, this is h minus 2e is movable because there's two divisors in this linear system, h minus 2e. So these are x3 equals 0 and x4 equals 0. These are two divisors in there. So the intersect. So the base locus of this has codimension at least of this linear system has codimension at least 2, which means that the divisor is not movable by definition. Okay, so this means, okay, so what does this mean? What does this mean? So I have that the movable, let me just write it down. So the movable cone of T is equal to the Neff cone of T union with some other chamber. And this other chamber is the Neff cone of T prime, some other variety. And according to Hu and Kiel, T prime is the only, let me write it like this, SQM of T. So T prime is the only small q factorial modification of T. There's no other. That's T prime, okay? So if let's just find one small modification of T, and we know that that gives you T prime. So I'm gonna write that quite explicitly. Okay. So how do I do this? So to go from T to T prime, I have to cross a wall. And to cross a wall, I have to tell you what are the contractions given by crossing this wall. So the contractions is given by this map, alpha, which is given by the linear system corresponding to this wall, which is h minus e. Okay. So this is a map that goes from T to some variety f, u x naught x4 goes to something. Now, what is this something? So I want the linear system, or actually the multiples of linear system of this divisor h minus e. So h minus e as degree, you know, it corresponds to all divisors with degree 1, 1. So what I want is all monomials that give me 1, 1 or multiples of 1, 1. So that give me, okay, actually let me put this here. Okay, so what are all the monomials that give me 1, 1 or multiples of 1, 1? So for sure, I have x1, x2. And then I have, sorry, this is a comma. Then I have u x0. This is a 1, 1. This has degree 1, 1. And I have u x4. And then I have x naught x3 and x naught x4, both of degree 2, 2, and all of these of degree 1, 1. Okay. I have T going to F by alpha. The question is, what does this contract? What is the locus here contracted? So I think it's quite clear that alpha contracts the locus This is an x3, by the way. Contracts the locus x3 equals x4 equals 0. Okay, because you have so these are multiples of x3, x4. This is x4 as well. Oh, so I don't mean x0 here. I mean ux3. Sorry. Okay. So it contracts the whole thing, this whole locus, x3 equals x4 equals 0, to a line, and this line, so let me write it, S goes to line gamma, which is isomorphic to P1, x1, x2. So I hope that this is clear. So I'm not doing anything fancy. I'm just saying that, you know, look at this map, alpha here. Just look at what happens when x3 equals x4 equals 0, and you see that everything goes to 0 except x1 and x2. So it contracts this surface to this line. So what is this surface? So I just have to erase this part because it's x3, x4 equals 0. And this surface is 0, -1, 1, 0, 1, 1, 1, 1. Okay. Now we've seen this representation, this kind of representation for matrices, and we know what this is now. So, you know, this is. Let me use another color. This is a C-star action defining P3, P2. So this is a P2. And this is a C-star action defining a weighted blowup on P2, which happens to be the ordinary blowup. So blowup. So S is actually F1, which is the blowup of P2 at a point. Okay. So on the other side, so you have, this is the picture you have. Oops. Okay, so this is the picture you have. So you have S being contracted to gamma, but on the other side, you have also some kind of contraction from T prime to your variety F. Okay, this beta is given exactly by the same thing, and it contracts a different surface S prime. Let me just say what this surface is. So this surface is it's a P1 cross P1. Okay, you can do the same thing as I did before, and you say that in this case it was a blowup of P2 at a point. In this other case, well, you can just look at the matrix and see that you have two independent C-star actions defining P1 and P1. So it's a P1 cross P1. Okay, so this is what you have. So you have P4. You did a 1, 1, 2, 2 weighted blowup to get to T. And you did some small contraction of F1 to a line. Now, after this line, you extracted with beta to T prime another surface, which happened to be P1 cross P1. And this is your small q factorial modification. So tau is your small q factorial modification. Okay. Now, now you have to finish the link. You have to say, what is this? Okay, so to finish the link, what you have to do is, so what you've done now is you've constructed the weighted blowup of P4 at the point. You did a small modification, but how does it end? So this small modification is just the composition of this alpha and beta. But how does this end? So it ends by contracting this wall here. So it's a map given by a linear system of multiples of h minus 2e. So let me call it phi prime. And phi prime, as we said, is phi prime h minus 2e. from T prime to something. So again, what is this something? Let me put this here again. So this something, so h minus 2e is here. So I'm looking for monomials which are multiples of 1, 2, of monomials of degree 1, 2, such as x4 and x3. But these are the only two monomials that you can have. So T prime goes actually to P1, U x0, x4 goes to x3, x4. Okay, so this is exactly a Mori fiber space. Well, okay, this is a fibration, and the fibers, you can check, okay, I'm not gonna do it, but you can check that the fibers are isomorphic to 1, 1, 1, 2. So these are Fano varieties. So in particular, this is a Mori fiber space. So fine. So just to have the complete picture, this is what you have now. P1 and fiber is P1, 1, 1, 2. So this is a complete link that you have from P4 with the, starting with a very particular guy, so a 1, 1, 2, 2 weighted blowup. So I'm kind of running out of time, so let me just jump to the main theorem and say the following. So remember our problem, right? So our problem was you have a weighted blowup of P4, so an A, B, C, D weighted blowup of P4, and you want to understand what are the tuples, the 4 tuples that give you such a Sarkisov link. Okay, so you saw an example of one that gives you, but there's actually 421 other examples. Well, 420 other examples. Okay, this is the theorem. So let me write that down. Let phi T to P4 be a toric A, B, C, D weighted blowup of P4. Then phi initiates a Sarkisov link if and only if A, B, C, D is one of 421 tuples up to permutation. Okay. So Olivia, does this end at 50 or 11 or
11?
Okay, I won't take much longer anyway. Okay, so you have 400, well, you happen to have 421 tuples up to permutation. So, the same theorem for P3 is well, it's a very cute theorem. It says that, well, you have, so T P3, and this is a ABC weighted blowup, then ABC can be one of 4 tuples. Okay, so you can see how much it jumps. So I just want to give you a very, very brief idea of the proof, maybe. I mean, I cannot even call it like that. So as I was talking to Al right in the beginning of this talk, I asked him, because you have a Sarkisov link from P4, and this, in principle, will end up with it can end up either with the fibration, so either with a proper fibration or with a Fano variety or with a weighted projective space. So P4, let me call it A, B, C, D, E. And I think one. Yeah. So how many, and I was asking him, how many of these are there which are terminal and Q factorial? Well, the answer is right in the beginning. I don't remember. It's here. So there's 28,686 weighted projective spaces of dimension 4, which are terminal and Q factorial. There's this number of possibilities in principle. So it turns out that the fact that we need really to control the singularities along the way really, really restricts. So this restricts the possibilities. So the fact that the anti-canonical divisor needs to be in the interior and the fact that along the way we need to have terminal singularities all the time, it really brings down 28,686 to, well, 400 and, well, slightly less than 421 actually, because not all of them are weighted projective space, but are fibrations. But, you know, so I think I'll stop here. This is all. Thanks.